Great. Well, welcome everyone. Thanks for joining us. My name is Daniel Palmer, and I focus on growth and partnerships for HydroForecast here at Upstream Tech. Glad to have you all with us today, and welcome to our sort of most recent in a new webinar series that we're launching. Today, we're going to look at the Freshet season, and in particular, focus on a basin in Idaho and see what HydroForecast predicted for that snowmelt period over the past year. So I'll be guiding you sort of through the upfront before we dive in, just talking a little bit about who we are as a company and what we do with HydroForecast. And then from there, my colleague Laura is going to take over and actually get to the exciting part, looking at this past spring's Freshet in Idaho. So who we are. There are about 25 of us now at Upstream Tech. This picture is actually pretty outdated because I'm sure many of you have also not seen your colleagues for a year and a half or more. But our team's primarily comprised of folks with a wide range of experience. So we have, the people who build the technology, data scientists, software engineers, and then we also have a number of subject matter experts. So hydrologists, meteorologists, other folks with conservation experience and clean energy experience. And you'll sort of see in a second why the team composition is important for how we think about technology and how we think about bringing our work to be applicable for you all. So we have two products at Upstream Tech. We're going to focus today on HydroForecast. The other one is called Lens. And Lens is a tool that's useful for understanding how properties or landscapes are changing over time. And it uses a combination of satellite imagery, aerial imagery, and then in-person monitoring tools as well. And if you're interested in learning more about Lens, feel free to just shoot us a note and we can get you connected to the right people. But that brings us to HydroForecast. So right now we're working with dozens of organizations, both government agencies, conservation organizations, clean energy producers, tech companies, at about 330 or more than that forecast points. I think as of this morning, we currently forecast about 3.5 gigawatts of hydropower production. So for those of you in the hydropower world, I think today is National Hydropower Day. And I think we see our role as being important at understanding sort of that influence of energy production and environmental stewardship. And so that takes a number of forms, and we're excited to show you today, especially sort of what we're seeing in an area and how that can be useful for a range of decision makers. Without further ado, I'll give you a quick update on HydroForecast, and then we'll get to the exciting part. So at a high level, what we do with HydroForecast is we predict and we model stream flow volume and other things like temperature. Our secret sauce with HydroForecast is that we have, we think, more high quality data that goes into our model than just about anyone else can. And that allows us to predict more accurately what flows look like. And so in particular, we have some of the best weather forecasts in the world that are available globally. We bring in satellite data that can give pretty high resolution, near real time conditions within any basin. So understanding the different factors that are driving either flow or limited flow. And then wherever it's available, we bring in situ data as well. And we pull all of that into what we call a theory guided machine learning model, which is just to say that we use artificial intelligence and statistics to make sense of a huge amount of inputs and translate that into actual flows. We've trained the model on hundreds of basins over the globe to be able to do that. But where the theory guided part comes in, and that's what I was talking about with our team, is that we're not just statisticians, we're not just computer engineers. Our team also has a number of folks who have significant experience actually working in hydrology and working in meteorology. And so we're able then to constrain our models in a way that we make sure that they actually align with what we know to be true about the real world and about hydrology. The way that I like to think about HydroForecast is sort of as an analog or the next generation of gauges. So if you think of gauges as the standard state of the art for understanding flow in a river. The main drawbacks are oftentimes you might want to know flow at a place where there isn't a gauge, so they're not always present. Even when you have gauges, sometimes you actually can't get high quality data from them. Rivers freeze, sometimes conditions in a river change, so the gauge isn't giving you accurate data. And then other times they can also just be looking at most up to the present. HydroForecast, on the other hand, is available anywhere. So we don't need to actually put any hardware into a river to create models. And we're able to do so anywhere in the globe. HydroForecast is highly accurate and it's reliable. It doesn't freeze, it doesn't go out. And we're able to look both backwards as well as into the future. The way that we think of this in terms of sort of specific offerings for our users and our partners is based on that timeline of sort of looking back versus looking into the future. So for understanding what's happened in the past, we have our historical reanalysis tool, and that can remodel flows that have happened dating back to 2000. So we can create a record of, at a specific point, what have those flows been from 2000 until now. We can do that both for what flows actually looked like, as well as sort of masking some data for the model and showing it what flows would look like if there weren't any impairments. And that can be a helpful comparison tool. What we're going to focus on today is our short-term model, which provides forecasts for every hour of the next 10 days. And so you get very high fidelity and high accuracy for that short-term period when really granular decisions are important. And then we have a seasonal model that looks more months ahead to understand what flows are expected to look like and how that compares to the range of historical averages. But without further ado, I will turn it over now to Laura to do some storytelling and talk through this spring's Freshet. Thanks.
Thanks, Daniel. Welcome, everyone. Excited to go on a journey with you into one of the basins that we are forecasting at as a part of this CIADI Forecast Rodeo, which is a national competition of inflow forecasting across 19 difficult to forecast basins in the US. And one of those areas is the North Fork Clearwater River, which has its outlet at the Dworshak Reservoir. And the Dworshak Dam is a hydropower producing dam at the bottom of that. And eventually this river drains into the Columbia. So it's important for headwaters, and it's a relatively natural basin. And so today we'll dig into what our forecasts did over this year's Freshet, and as well as understand why the model is doing what it's doing based on the inputs. So we like to think about streamflow signatures, or I like to think about, at a basin, at a gauge, the gauge in the model is telling a story. And so depending on where you are, your geography, your topography, and all of that, you may have a different signature that goes along with the hydrology in your basin. And here I'm just showing the observational record at the outlet of that basin near the Dworshak Dam. And this is from the USGS, it's daily flow. And we can see two freshets here, the 2020 spring melt and then this year's 2021. And just a few things to qualitatively notice that I see. There's a couple of periods within the melt that we sort of refreeze, or that melting slows down a bit. And so those can be important for making short-term operational decisions, releasing water, storing water, things like that. And then also just that we have a big period when it goes dry throughout the fall, a few rain events, maybe even rain on snow in the winter. This period here, if you can see my mouse, was this winter in January, and the gauge actually went out. So there was no observation during this time period. And that can be something that happens commonly during winters or thaw out if you have a thaw out in your river, ice jam, something like that. And so that can be, especially in the northern basins, an uncertain time. Can you rely on your gauge? And so next I'll try and add the long-term median. So these gray points they're going to repeat every year. So this is the long-term median for that day as you move through the historic record of the observations. And in this basin, because we're in a relatively reliable, or at least historically reliable, spring melt and then dry period, the long-term median captures the pattern of that pulse and then drop quite well. Now, of course, we can notice sometimes when it may overpredict or underpredict. The question is, how much better can a forecast do than the long-term median? Because the free, easiest thing to do may be to use your long-term average or long-term median as your predictor for the next few days or for the next few months. So I'm going to add the HydroForecast mean prediction on top of this. And so what we did to produce this plot was we have our lead time of 24 hours ahead. So this is like the day ahead forecast. And then we string all of those together to make a continuous time series. And so for every single day ahead, this is what HydroForecast produced over this sort of 1.5-year period. And so a few things, oops, I jumped the gun. A few things to notice here. The forecast can actually pick up on those peaks and troughs that occur not only sort of within one event or two events, and also during the melting pulse, but really get this rise well. And so that can be important for those operational or 1 to 10 day decisions. Another thing I notice is this peak that sticks out here. We don't actually know what the observation was. It's very well possible that there was an event and that our model was able to predict it and didn't need the observation or to assimilate, or didn't need that, didn't rely on that gauge for anything. And so we're still producing forecasts even if the gauge goes out. And then also able to pick up the differences between the 2 years. And so if you're just using the long-term average, you may overpredict in a dry year and you may underpredict in a wet year. So then the teaser that I already shown on accident is that with our forecasts, we also produce confidence bounds. And so every forecast, because of our neural network model infrastructure, we're predicting a full probabilistic output at every time step. And so here we just choose to add on the 50 and 90 confidence bounds to show around our forecasts, but we can produce any of those, 10, 40, 60, whatever our customers or folks are interested in seeing. And so with that, you get really a nice sense of when the model is more certain. And usually the times that the confidence bands widen is a time when the precipitation that goes into our model is not agreeing. And so we'll get into that a little bit more, but we use multiple precipitation inputs because we know precipitation can vary and is uncertain. And at times when that agrees, the model is more confident. And then at times when that doesn't agree, typically, and also times where the temperature is hovering around freezing, we get a little bit more uncertainty, which is reflective of the real conditions. And so this is essentially what's happened in the North Fork Clear River this year. A little bit less of a freshet than what happened last year. And that's what we've seen throughout the West and Intermountain West. I want to point out one other thing that our forecast can do, because we can show an output or give an output on an hourly timescale. What happens in snowy basins during the melt is that you have this diurnal pulsing where, in a given day, the temperature in the sun comes out, it warms things, melting accelerates. And then as you're hovering around freezing, you may not get any melt at night if the temperature goes low enough. And so we see that pulsing that occurs. And that can also be important for shorter term decisions and understanding the partitioning between, if it rains and it's wetter or warmer, how much of that is going to go into melt and runoff. And so our model is really picking up on even that detailed signal here, whereas daily models and also long-term averages are not going to be able to pick up on those details. So I wanted to start with this kind of broad overview of what our model did on the Freshet timeline. And one thing that I wanted to point out that the model is seeing, and we'll go into inputs a little bit more, is this is one piece of the Dworshak basin, one piece of the North Fork Clearwater River. And what I'm showing over here is some of the satellite inputs that we give our model. And so this top one is NDSI. It's a snow index from MODIS. and the bottom one is NDVI. It's a vegetation index from MODIS. And these are near daily pictures of our basin. And what happens is we're showing the model these pictures almost every day, and it's telling it how to interpret the fact that here white is snow and blue is not snow. And down here, green is vegetation or chlorophyll it's picking up on, whereas brown can be kind of barren or just dead area. And so as you move from, let's say, February here over to July, the snow is melting, and the model is then picking up on that and learning how to interpret that signal alongside showing it the vegetation index, where in February we have a lot of barren ground. And then by the time we get to July, the whole thing is greened up. And so by feeding in all of these different data, the model then tracks different signals like snow melt and how to interpret that as soil moisture and then runoff and infiltration and things like that. And that's the way that the neural network model can really interpret these different pieces of data. It's a little bit different than a process model where you would write the equation out for understanding how much water would go into the soil versus runoff. So another thing I wanted to do in the webinar is to show what our dashboard looks like if you were a customer and how we string together different forecasts. And so I'm going to show a demo dashboard here. This is for our webinar. And these are 3 CIADI sites that we're forecasting at. And one thing to note here is the black line is the observation, and the purple dots, those are the long-term medians. And depending on where you are, the long-term median can be a good predictor over the snowmelt season. It can also not be a great predictor for the snowmelt season. And so just to show that that will vary by site. And so this is the dashboard that it's a web-based dashboard that we provide for our customers. And if you have multiple sites, each of your sites would show up here. And then you can go in and view particular sites. So we'll go into Dworshak and view it. And so then I want to add on some of the forecasts. So, if you signed on and you were a subscriber, you would have access to the full archive of forecasts since you sign on. And here I just have preloaded a couple so that you can scroll down many sites. So we just have one time period selected here, and I wanted to show you how these 10-day forecasts can kind of be strung together. And so if I just add on these lines, yeah. Sorry, I'm just noticing. I'm going to zoom in to the period of the melt that's like the most earnest. And so you see here, there's a clear increase in runoff and melt. And so that's one of the more interesting time periods. And so another thing you can do in our dashboard is you can kind of hand select what time period you're interested in and zoom in on it. I'm actually going to turn off this one for now. So what I'm showing here is just the evolution of a 10-day forecast. And sorry for the, as I move this box updates and moves along with me, but it can be really helpful for if you're interested in here's the observed and here's the model, what's the difference at this particular timestamp. But the point here is that, as we string together these 10-day forecasts, and so our forecasts are updating every day. And the idea is that, of course, as you update the forecast is going to get better at that lead time ahead of you. But here's to show kind of what happened over that earnest melt period between late April and the middle of May. And so the forecast is pretty well able, this is just a single trace that extends the whole 10-day. So even out to this 6 to 7 day period, the model knew that we would be experiencing this big rise in the melt. And that's likely related to a temperature increase going from hovering below freezing to just above freezing. And so then following the next trace, we see there's another kind of pulse here for another peak, another sort of mini peak. And then the model also knew to recede down. Of course, when you get to the end of the 10 days, it is common for there to be a bit of a drift in the forecast, especially if something is happening in the inputs. And so another thing I wanted to show is sort of how that evolves in our forecast. So here I'm going to zoom in even more and turn on just these May 12th, 13th, 15th, 16th, 17th, because what I want to show here is, all right, so we start out with the green line on the 12th, and the model is able to pick up that diurnal signal pretty well and stay, and then the observations are trailing that. Then on the next day, we issue another forecast on the 13th, and you can see that that forecast by the end is actually doing a bit better on days 8 and 9 because it's been assimilating observations, and the inputs in the precipitation and temperature forecasts are also getting better. The same thing happens out here if you look at, like, we issued this forecast on the 17th. So we're able to get the magnitude of this peak much better than the forecast that was issued way back on the 12th and 13th. And so that's what we like to see. We like to see that the model actually trends toward being more accurate as the forecasts update. That's important for making sure that the model is learning hydrology and picking up on using its inputs appropriately. And so again, you have, if you were to come into the dashboard, you can show hourly or daily data. You can zoom in and really try and dissect what's happening with the model during these important periods. Another facet of this that we use in addition to the streamflow forecasts is the actual inputs. And so if I just go down here for Dworshak, we're also providing precipitation forecasts information and temperature, as well as some other inputs. And what you can start to see here is during certain times, the precipitation forecasts, these are from ECMWF and from GFS, they can disagree. And so that's when the model knows to widen those confidence bounds. And also around the time that the temperatures are hovering around 0, that will cause the model to respond and maybe widen its confidence bounds. And so that's one of the ways that we put together the story of why the model is doing what it's doing, is we are able to, and we want our customers to be able to go in and actually interpret a lot of the input data to understand the response in the streamflow. Cool. If I pop back over to our slides, just finish up here and then have some time for questions and answers. Just to review this site in terms of CIADI. So for CIADI, we are forecasting against other public and also private operational forecasting systems. One of them is the NOAA RFCs, another is the National Water Model. And so just looking out at this particular site over the 1 to 3 day, 4 to 7 day, 6 to 10, and then all of it together in this last column. There are a number of metrics that the competition is tracking. One of them is the Nash-Sut cliff efficiency. And that metric, if you have a 1, then that means your observation and your model perfectly match. And so 1 is the perfect score. Anything negative means that you might as well have used the mean and you don't need a model. And so we like our numbers to be closer to 1. And what we find here and pretty consistently across other sites is that our model is not only maybe more accurate on the shorter term, but is able to maintain that accuracy even moving out to 6 to 10, 8 to 10 days. Compared with the other alternative options. And so this CIADI forecast rodeo comes to an end in October, and we'll see if we're still maintaining these numbers by then. I think so, since the most active period is already over here. So I think just to put our model into an infographic slide, just for a summary, how does a model know how to do these things? How does it learn to tell these stories? As Daniel mentioned in the beginning, essentially what we do is we have a core model that we provide satellite observations, weather forecasts. If we're looking at seasonal forecasts, then we're going to be using some of those climate indices and things that are happening on those relevant longer term timescales, as well as any local information from gauges that is basin specific. And so our cloud and automated production line puts together all the data, processes it, makes it into a nice package. And that happens across hundreds and hundreds of basins in the US and now expanding beyond the US. And so because the core model has seen many, many different types of hydrology, when we go to a new area, gauged or ungauged, we're able to make a pretty accurate prediction using any local information that we're pulling out from the satellites and weather and all of that. And so our approach really is to build a very, very strong core model so that when we have new customers and new clients, we can go in relatively quickly and spin up in the new areas. And then we come out with our predictions. So I think last slide here just related to what does this mean? Why are forecasts important in this North Fork Clearwater Basin? This basin has the world's largest steelhead trout hatchery. So a line of our customers that are more focused on conservation use our model to understand past flows and how environmental flow policies can be developed for fish, for habitat, for ecology in general. And so this is an important basin for fish. Another point is that there's 400 megawatts of power coming out of this area, coming out of this dam. And that means that operating more efficiently and not having to spill, and also being able to use hydropower as the flexible asset that it is, forecasts are very important for being able to do that. And then the last point I want to make here is just, this is a tributary of a tributary of a tributary to the Columbia River. And those headwater basins are just so important for being able to plan on how much water is available as you move downstream in important big basins like the Columbia. So having a good understanding of what's coming can really help inform management and allocation as you move further and further downstream. So I think that's it for the story of the North Fork Clearwater for now. Thank you, and happy to answer any questions.
Awesome. So we've had a couple questions come in so far, a couple in the Q&A and then some privately. Let's maybe start with a few of these from the Q&A. So could you go back to the storytelling summary of the past freshet? And the question was, why is the median of flows not smoother? It seems to suggest that freshets occur on same dates in multiple years.
So we're talking about this slide?
Yeah, I think that would be great.
So I think to understand the question, why is it not a smoother? Well, first of all, these are points. We maybe could have had it as a line, but do you mean why is the median, the long-term median, not less jagged?
Yeah, I think the question, as I understand it, is maybe how we're defining the long-term median. And so my understanding, and feel free if you ask this question to pop back in the Q&A and ask separately, but you'll see that the points of the long-term median are the same for 2020 as they are for 2021.
Yeah, this point's probably the easiest one to look at because it's above 20K.
Yeah, exactly. So it's not that the freshet is occurring on the same dates in multiple years, but these dots, each one is saying for that date, what were the median flows over the past X years? And so it's predicting it as if it were on the same date because that's a historical average.
It's a daily long-term median, if that makes it clear.
Yep, great. And then the second question, if you can jump to the satellite image slides.
Yes.
They're noticing that the images have straight sides rather than following the watershed boundaries. And they just wanted to confirm that this is for illustration and not how the computation is actually done.
Yeah, I'm just showing a cutout around the river. This is not the actual drainage basin. The actual drainage basin is on that first slide I showed of the image. So we just cut out a piece of it to show for illustration. Yep.
Great. Another question we had was around how well HydroForecast can predict irregular events or events that the basin hasn't seen before.
Yeah, and that's a great question. Because we are providing dynamic data to the model, in other words, a lot of the challenges of a process model that you need to calibrate and provide, an image of what is the land cover and things like that. If you were to say have a forest fire in that area, or if you were to have something that was a reflection of a disturbance, those type of models, in my opinion and experience, have a lot of trouble capturing those dynamic changes in a basin, whereas our approach actually embedded in it is the ability to capture those dynamic conditions and things that have not happened before. And so because we're using really high resolution land and weather forecasts, we are able to pick up on those peaks that have not been seen in the observations, as well as the low flows that have not been seen.
Excellent. Another question we had was how long the calibration period was for HydroForecast at this basin in the North Fork, and if we also run seasonal forecasts for the basin.
Yeah, so for this, for the CIADI, the model was trained from 2015 to 2019. And then our validation period was March of 2019 through March of 2020. So actually everything that we show in the plots here is actually during the validation period where the model didn't see any observations, had no information about what was occurring. And this is how the model validated there. And so in general, we can train on 5 or more years if needed, and then we try and validate on 2-ish years. And then at this location, we have not set up a seasonal forecast since CIADI, we set this up for CIADI, and CIADI is only interested in the short-term forecast. So we just have the 1 to 10 day running right now.
Got it. And could you just, since it's a little small on the screen, could you showcase a little bit more of on this LTA versus the observed forecast or the observations during this period, how far off, where you just were, yeah, how far off does the average get from what we're actually seeing? It looks like the general trends are close, but what are the units for that discrepancy?
So we're in cubic feet per second here. And I guess if you just pick out a couple time periods, like during a bigger peak, you know, the long-term median is down around 10,000, maybe 11,000, when the peak is up to, I don't know if that's 18 or 19 or 20, 21,000. So that can make a big difference if you're using the past to, predict what's happening on a daily or day ahead basis, let's say for trading purposes of energy, as well as flood planning if you are concerned with that for your reservoir.
Great. Another question, there are 2 I'll start with. The first one is satellite images and other static inputs are not time series parameters. So how do we pre-process these inputs to combine them with other time series meteorological data? And does this mean that the static values were repeated every time step?
Yeah, so the details of the actual data processing in the pipeline, I'm not going to be able to speak too clearly about, but that's something for sure to send us an email about. But essentially we have a set of static inputs, and that's things like the topography, it's probably relatively static, and just the general basin itself. And then that is fed in just as one time. And then we have all of the land surface and land images that are actually updating. So all of those MODIS pictures are updating almost daily. And so the model is seeing that daily. And it's also, so it's seeing it at that frequency. It's also seeing weather forecast information, even more frequent than that. So we give it every time the ECMWF and the NOAA GFS and GEFS provide an updated forecast, we have a way to ingest that data. And so all of that is kind of built into our data pipeline that's all processing on the cloud. And so that's happening. And then our model runs, produces its forecasts, and then we send that out to the dashboard as well as to an API for our customers to pull from.
Excellent. And then the follow-up question on that was, with the use of satellite images, does this mean that HydroForecast uses CNN to analyze the model? And if yes, maybe Laura, could you explain what CNN is for folks? And if that's a more detailed question for us to answer offline, we'd be happy to do that as well.
Yeah, I think we should probably move that one for someone on our Eng team to answer. Perfect. I don't know the details of using CNN versus using just our normal neural network and all of that. So
Great. And then we got one other question around you mentioned a Siati rodeo a couple times. Could you explain a little bit more about sort of what that is and why we're participating and why it matters?
Sure, yeah. So the Siati is a group of they have a hydropower group called HOPIG, and those are industry members, and as well as they coordinate with some like Bureau of Reclamation and other entities as a sort of, I don't know what you call it, like an affinity group or an industry group. And the Bureau of Reclamation, in conjunction with this group and others, put together a competition for 1 year. And that is a public competition for anyone to join and actually produce forecasts. And the idea is that for those individuals who kind of tinker around and have a model, they could win a cash prize for having the best forecast. And so that's the public side. Then there's the HOPIG or Siati side, and that is for operational systems like ours and for the RFCs and for the National Water Model and other private industries to submit their forecasts and sort of see how well they do against the top producers or against the public entities. And so that's why we joined in on that side of the competition, and we're forecasting at 19 sites. That's how many there are, and they span from the west to the east coast, north to south. And so in this competition, our model is being tested essentially at every different type of hydrology, small, big basins, snowy, rain-fed, et cetera. And we're able to actually put our model to the test and see how well it does against the public and then private competitors. And the competition again ends in a week, but so far we are doing really well across the different basins and different locations. And I don't know, I can't say that we're winning because I'm not the judge of the competition, but suffice it to say that across all the different sites, we have we're doing quite well, and we're excited to see how that ends up.
And I would just add that part of the reason behind this whole forecast rodeo as they have is that, as I'm sure many of you see in your day-to-day work, historical patterns for water flows are just not actually holding true anymore. Even during the short period of this competition and our models training for it, we've seen historically high flows that are significant floods. We're seeing pretty serious droughts. And so I think there's a question overall of, can models like ours that use artificial intelligence and machine learning, can they be a useful tool in the toolkit of folks who really need to make important decisions around conservation and flood management and energy production? And so a big part of this competition is let's actually go out and test that, and let's test it at places that are different from each other and hard to forecast. And so we've been really excited to be a part of that overall evaluation. And I think that's why you see folks like the Bureau of Reclamation and the Department of Energy and TVA and other folks like that really involved. So all that's to say, stay tuned because we'll be really excited to see some of those results in a couple of weeks or a couple of months, I guess is probably the better timeline. One final question, I know we're wrapping up on time, is whether HydroForecast considered artificial structures in its study areas, so things like dams or other impairments, and how we've approached that so far.
Yeah, great question. We're working with the Nature Conservancy in California to test out how well our model does in impaired, or I don't call them impaired, but in basins that have human influence or are unnatural. And so we're doing this across the entire state, and we're actually training a core model across the whole US using enhanced basin characteristics. So that's like flow alteration characteristics, both in the geomorphology as well as dams and diversions and things like that, including all of that in our core model, and then validating or evaluating it in California. And so far we're seeing really good results, especially below dams. And what's amazing about that is that in this case, the model was trained on only data outside California, never had seen any of the data it's being evaluated on, and it's still able to pick up those patterns as if it was being given data from that site. And so we actually think that there's a lot of potential in using our core model to work in altered basins and basins where there are impairments.
Awesome. Thanks, Laura. And since we have a couple minutes left, one last question that we'll run through and then we'll close up. But I thought it was especially relevant for the conversation was, given that we're seeing changes in hydrology compared to the past, does the model include any forgetting of older observations, which cause newer observations to be weighted more highly? Or to put another spin on it, how do we actually ensure that we're understanding what's happening in a basin recently, if that's different than the past?
Yeah, great point, great question. So one of our things that we do is we go back to the year 2000. That's essentially when those satellites came online and we're able to take the high resolution pictures and provide those inputs. And so that's really, if we're able to go back that far, we are only picking up those conditions and using that in our training. We're usually training on the closest period to now, right before validation. So as I mentioned, we have been training between 2015 and 2019. And so that's really, and we can change that period. So if there's a period that's less or more representative, we can select that period to train or to validate against. If there's a period that you would be concerned, the model wouldn't be able to do well, we can sort of move that around based on the data available. But I think it's a really good point of saying, like, in a basin, there can be a time when you had a big land use change, maybe urbanized, and now going back beyond some point is no longer reflective of the conditions. And so we're able to actually do that by selecting the historic period and training period that we use.
Yeah, and I think to add on to that, one thing that at least I've found unique about our approach is that because HydroForecast is trained across hundreds of basins, and it's pulling in things like the current, we were talking about the different satellite images and the current weather forecasts, it's not just trying to say what has happened in this basin before, and is that going to happen again? As much as it's saying, with all of this information that I'm seeing about the conditions right now, what would I predict flows to look like? So if the basin is different now than it was 20 years ago, the model is going to be seeing those current basin conditions, and it's going to know how to handle that from the other basins that it's seen before. And so I think that's one piece that has helped us, at least so far, be able to calibrate to new conditions in a basin without a very lengthy period of going back and manually adjusting different statuses within that model. So with that, maybe Laura, could you flip to the last slide just so folks know? If you have any other questions or want to chat further, we'd really love to talk. You can email us here at team@hydroforecast.com, or if you go to our website, it's really easy to contact us as well. But thanks, everyone. Really appreciate you coming and hope you have a nice rest of your day. Bye.
Thanks, everyone.